So yeah, I'm Philippe. Even though I have a Dutch name, actually I'm from Belgium. So yeah, I have a Dutch name living in Netherlands, but I'm from Belgium. So yeah, I work in Utrecht with Eric van Sebille, and we're working on tracking the plastics in the ocean and see where it comes from, where it goes, trying to understand what's the distribution of the plastic contamination. But today I will speak just a bit about plastics. I'll mostly speak about parcels. Do we see the laser? Okay. I'll speak a bit about parcels, which is the model we developed to track this plastic. And I will focus on the interpolation schemes and a bit about efficiency. So what are we doing? In Utrecht, so we want to study where the plastic goes, but we don't have any boat, we don't have cool labs, but we have computers. So what do? We release virtual particles. So here we release particles in the Rhine and the Thames estuaries, as an example. And then we track them. So we take as an input some flow field data from other data sets. So we don't compute the flow field, but we use the flow field and we transport the plastic. So here basically it goes towards northeast, it follows the coast, it follows the Danish coast and it enters this strait and it continues along the Norwegian coast before reaching the Arctic. And there is a lot of deposition, so a lot of plastic being trapped along the coast, especially close to the setting points, also in the fjords. And then there is a lot of accumulation of plastics in the Arctic when it gets it gets stuck there based to the currents, but there is still some currents pushing around, so we have some plastics reaching the West Atlantic, even if it's still that's the problem also with the scar plot. We can see it later. Basically, the most accumulation zones is here and along the coast. We have some plastics here, but which is not really important to comparing to the other one. So this is kind of examples of runs that we want to do with parcels. And how we do that, so how do we use parcels? What is parcels? Is the next slide. So parcels is quite easy. It's quite different from what we've seen from XGCM before. So it's again some post-processing of data. So we have some gridded data from other models. So it's important that it's not a cloud of data, it's gridded data. We have a field set, then we import it. And unlike XGCM, we'll also perform some computation on it, but it won't be a gridded computation. So we won't have a grid for the vorticity of the divergence. We'll have just a set of particles. So the particles, they can represent plastic, but whatever other quantities, can be the water mass or some contaminants or whatever. And the parcels, we just deal with this particle set and find for every particle where it is located on the grid. So if our particle is here, we just take all the grid points in the neighborhood of our particle, and then interpolate the value at this grid to compute what's the flow field of the particles, and then just advect the particles. When I say the flow field, actually it's not only, so the field set can be whatever. So it will be the flow field, but for plastics modeling, for example, the surveys, it can also be transported by the wind stress, by the Stokes drift. So the Stokes is the transport which is induced by the waves. We can also take into account any other kind of gridded data. For example, we could say, I don't know, so some kind of fish doesn't like when it's too warm, so the fish is swimming at the surface, and if it's too warm, it just dips. So a kernel, which is the kernel is what's defined by the user. So an important kernel is really to say follow the flow field, but a kernel could be if temperature is too warm, just sink. So it's really user-defined, easy kernel, which is developed, implemented by the user in Python. So the two important party in parcels is write a kernel, then we induce the dynamics of your particle, and interpolate the gridded data. And I would focus a bit on this gridded data. So we can see it here. So basically, our particle is within a cell, and we have some data at the four corners of the cell, and then we interpolate the value. So for people who are not familiar to numerics, it's quite easy. We just basically we take for this particle, we take the flow field, like the further away you are from the grid cell, the less important it is. So here you see the importance of these nodes just decreased with space, and basically so you can bilinearly interpolate the field at the particle position. So this is done by SciPy and by most of the interpolation schemes, and it works really fine. Also, so with parcels, we can read different kind of data. Also, like structured data, but they don't have to be rectilinear. They can be curvilinear grids. And in the vertical direction, we can also use Z level. So when we have the non-constant number of layers, or sigma levels when we have a constant number of layers, but with the depth increasing. And then, as in XGCM, there are different kinds of data. So the example I've shown before, so they were the A grid, but for most of the modern model now, they use other kind of grids as a B grid or C grid, and we've already seen it before. So a C grid is a staggered grid when the U velocities are not at the same place as the V velocities, and the tracer at some other point. And then the question is how to interpret this data correctly. So if you use a SciPy, I'll show you just later what you can do. And actually, on this simple example, so I have just a simple academical example. We say when you have just the water goes from the left, it goes up here, and on the right side it goes down. So I've just defined this simple analytical flow. And then we want to try to reproduce this flow by using greedy data. So we have just those two cells with the A grid, and we have 6 values for the velocities, and we can interpolate those velocities, and we recompute the flow. So this one is not analytical, but it's been done just by interpolating the flow field for each particle. So the line is just the trajectory of every particle. Then what happens for a C grid? So for a C grid, the red points are the U velocities, the green points are the V velocities, and what you can see a C grid as a set of two A staggered grids. So like for the U velocities, you see those 2 points here. You can also just draw like a full grid, and you could interpolate the velocities also, like the U velocity here using those 4 values, and this cell using those 4 values, and so on. So that would be for the U velocity. And then you do the same for the V velocity. So you had those points, but you can also stagger all the V velocity, and you have the V cells. So you have the U grid, the V grid, and if you interpolate that, you obtain this trajectory. So you see that you completely mislead you have a misinterpolation. I don't know if this word exists, but basically you completely miss the flow. You still have the plastics going somewhere in the similar trajectory, but you completely miss the boundary layer and important properties of your dynamics. So you cannot do this just reading your series as 2 A grids. As we've seen in the talk before, like if you have built those C grids, it's for some reason, like they have some nice properties, especially for like a volume transport, and we want to take that as those properties. And basically, what people were using before, like for example, in earlier version of Parcels, they were just using a SciPy interpolator with interpolating the U velocity on the U grid, the V velocity on the V grid, and the flow field works. There is something, there is something happening with the particles, but it's wrong. It's not the trajectory that we expect. So what are we doing? It's way easier actually. So on our grid, if you have the U velocities on the left and right edges, and the V velocity on the other one, we can simply interpolate linearly those flows, and we respect like the finite volume schemes when you have the transport on these cells comes from this side, on this side goes upward. So you respect the discretization, the idea of the C grid. Of course, you have to watch out what happens in a curvilinear grids, and for this, basically, if you have a grid which is not a nice quad but like a structure rectangular, you have to remap this rectangular to a square, and with this you also take into account that the velocity. The velocity here also push a bit southward your particles, and this also works in 3D. So if you have a structure hexahedron, you can also remap it to a cube, and you can correctly, conservatively and consistently transport your particles in a unstructured C grid. And if you follow the C grid, you will also retake the perfectly analytical flow. Yeah, I've built the flow to be this way, so it's not really a surprise. But basically, that's what we want to use a C grid interpolator, which are missing in X-array. So far we are interpolating. We have our own interpolation schemes, but that was a question before. But that should be something that we should have more freedom in X-array. We would like to put our schemes into X-array and to see how to not give up on X-array, but to use it better to to use the full potential of the library. But then, I will stop here with the interpolation schemes and going a bit about efficiency. So how we do is to interpolate the particles. So I've shown just a few particles, but the idea is to track millions or billions of particles. And also that's one challenge, to have a lot of particles. And the other challenge, as Ryan has said before, is we have more and more data. So here are I'm using just 1/12 resolution data. It works fine, but we would like to go 100. So we would like to go to 1 kilometer of further resolution data. And then that's the second challenge, to how to go with a lot of data. So there are different ideas. So using SciPy, Xarray. The good point is it's easy to implement, because we are in the Python framework. We can also use Xarray data lazy loading, so we don't care so much about the size of the data. Everything is done for you. But for our particles, it's still quite slow actually. So the SciPy interpolator, we are not fully happy with that, especially because we have to rewrite the interpolation. But still, we have some limitation there. Then we could use Dask. We've tried it a bit. We've given him some try, but there is still some development to do there. So it's still somehow easy. No, not that easy for me. I have seen problem with HPC, but also the main difference between what we do here and what's been done at GCM is we don't compute we do not compute a graded versus. We don't compute graded divergence or other data on a full data, but we have just a cloud of points, and we want to see what's going on there. So it's a bit harder to distribute what to do where. So we could distribute a lot of tasks, but for some particles which are located one to each other, close to each other, we would like them to be also on the same task, such that we don't load a few times the same data. So there is something to do there, and so far we don't use correctly the Dask in Parcels. What we've been trying recently, so I've been developing an MPI implementation. So this is less easy. You have to do the work by yourself, but the good point, you have more control over what you're doing. And also the problem with Dask, it was harder to use the C code, and that's something important for us, we showed before, just in the next slide. We use also the C. So Python, Parcels is implemented in Python. So we have all the full structure of Parcels is the following. So we load a field set in Python, then we can do some post-processing of the data in Xarray. We create our particle set. So having a set of lot of particles and saying what are the important quantities for every particle. So of course, a particle has quantities such as its position, its time. But you can also have the age of the particle. If your particle is plastic, you could have the type of plastic. If it's plankton, you can see if it's dead or alive. So you can have a lot of state variables for your particles. You create all of that in Python. Then you create your kernel. So the kernel is really inducing the dynamics. You also write in Python. And then you have your time loop. So the time loop is adding particles, updating the field sets if you want to change something, or loading new time steps, exporting data, and the inner time loop. The inner time loop is where the real computation is done. And this is the one which is done in C. So in C, what do we do at a lower level? First, we interpolate in a C mode. We interpolate all the data, and we execute the kernels. So the kernels have been translated just in time from Python to C. And then, of course, some post-processing also done in Parcels, so in Python. But so the C part also, we also have a full Python version, but which is still way slower. So we're working on first having something faster in general in C, and also we would like to have not such a big difference between the Python version and the full Python version and the Python C version. A bit more about the efficiency. So that's what we were working on with this MPI. The version is really how to distribute the data. So basically here I have just a sketch of how we work with two processors. So we want to distribute our orange particles and the particles of the dots between the processor orange and processor blue. And then when we pass from Python to C, we lose the lazy loading of Xarray. So we have to give we have to say to C where is the data. So the data has to be loaded into memory. So what we do is we convert from Xarray to NumPy array part of the data, just chunk by chunk. So we only load the chunks where some particles are. And then there is some balancing to do. So for example, here, you would like the free blue dots, the free blue particles to be sent to the orange processor, and the orange processor to be sent to the orange particles to be sent to the blue processors. So you don't want to load twice the data. So that's what we are working on for the moment. There is a proof of concept. It works quite fine, but there is a lot of developing to do. So some really smaller results. So you see, like in terms of scaling, when you put more and more particles, so you have a linear linearly increasing time of computation, which makes sense. You would like to have more and more you don't want to have a quadratic time when you increase the number of particles. But of course, at the beginning, so this is like a particle dominating application, while at the beginning it's more the field set which is dominating the cost of the flow. And this difference between this behavior and this behavior will depend depending on the number of particles and of course the size of the field set. So you would like the field set to be less and less important, and try to see to design the field set as cheap as possible, such that as quick as possible to reach the linear upscaling of the particles. And then the MPI scaling, so it works quite fine. So I've just a few weeks ago I've done a few simulations up to hundreds of processors, when we see quite a good but not perfect scaling of the execution loop. So the time loop when we execute all the particles, it's some fair scaling, but the global scaling of our application is really dramatically bad. So at the initial guess, when we define, given all of particles, what are we gonna send to the orange the orange processor, and what we're gonna send to the blue processor, so far it's really slow. So we use a scikit-learn for that. We had to do something better. There was this option with GPUs, but also I think just another design we should watch out. So there is some work to do that. So this overall red curve then show the global speedup, which is completely wrong. That will be improve. That's a number one task that should be done in a few weeks. So far the initial distribution of the particles is dominating at some point the runs. Except if you run for ages, of course. If you run for long enough time, then the red curve will reach the blue one. Okay, a bit of applications, because there was the plastic word in the title, so we want to talk more about particles in general. So we do some plastics applications. We use Parcels to release particles everywhere in the ocean to let it run for, I think it was 10 years here, and then we see those garbage patches accumulate, the plastic accumulating the garbage patches at the surface in the ocean at all the subtropical gyres in all the basins of the ocean. So this is quite well understood phenomenon now, but so we can do this with Parcels, but this is like the surface plastics. It's only account for 1% of the plastic. There is a lot of work to do to still understand what's 99% of the plastic that at some point sinks due to vertical mixing, the turbulence, also due to biofouling. So when the organism attached to a plastic particles, so there is a lot of research to do there. And we use it with Parcels. But another application was just to find the origins of the plastics ending up in the Galapagos. So there are some runs also to see where it could come from on the South American coast. You can see if you track it back. I'm not a big fan, but you can track back using Lagrangian modeling. And you can see also where it comes from, where it could, how much it travels around the Antarctica using the circumpolar Antarctic current. And then we don't use parts only for plastics. So here there is also some study to see dinocysts, which are a kind of plankton. So they find dinocysts in the mud or in the sediment on the ocean floor. And they want to know where this plankton was living, where it was living earlier. And of course, when it sinks, if it sinks really slowly, it can be transported like a few hundreds or thousands of kilometers. So we use Parcels also to find where it could be living. And this is used for paleoceanography as a proxy to find the past condition of the ocean. And another example is some tuna fish. So tuna, of course, they have some behavior, but they can be parameterized. And here they were using Parcels to So the tuna was following the currents, but it was also swimming to find a better environment. So basically, in terms of food, where it can find its food. So the tuna was following the gradient of a field, and it was also used. So basically, it was used to see how fisheries are really like playing with the dynamics to try to improve their fishing catch, but dramatically, they basically just empty the stock there. So it's quite dramatic what's happening there. But we can also use Parcels to see what are the strategy there. And to come back to the initial video, so Parcels is not attached to one general circulation model, so you can use data from a broad range of data sets. And here we're using the to see what's the sensitivity of those data. So we're using releasing particles, and here what we see is not particles anymore. It's the density of particles after 3 years of simulation, and you see a different run. So with one simulation at 1/12 resolution, the same run, the same original model, but at a 1/4 resolution, and you see what's the importance of a mesh resolution, how it affects. Then here we are nesting a small data set within a larger one to see if we could improve the quality in the North Sea region. The effect of stokes, so the effect of the waves which are transporting the plastic at the surface. So here there is a lot of waves going towards the northeast, so it induces much more beaching on the coast. And then some diffusion to account for unresolved processes. And the last one was some 3D runs. So all those were surface plastic, so the floating plastic. And if you take into account we don't ask the plastic to float anymore, but we really let it just as a passive tracer to follow the flow field. It behaves differently, especially in terms of the Baltic by a subsurface flow. And you can see the plastics reaching a really deep water. But this was really a academic test, so it was not showing 3D plastics. There's nothing about the buoyancy of the plastics. It was really to follow in 3D the flow field. All right, so as a quick conclusion, so we use Parcels in a large variety of applications. It can be plastic, but it can be whatever data that you use in whatever data, whatever tracer that you want to transport in a Lagrangian framework. Then a strength of Parcels, we can use a data feed from different kinds of formats and different kind of discretization, which is the huge point if you want to use a lot of data sets. And we are working so far on the efficiency. So it's working better and better, but there's still a lot of work to do, which will be the first job for the next few months. And also on a larger term, if we are looking for a postdoc to work also in Parcels. So if someone's looking for a postdoc, just please contact me or Eric. And you can see all the data of the model on GitHub. And also on this paper, it's already accessible on the net. But I have first it's in press now. But they completely messed up the proofread, so I have to correct all this done. So it will be still close. The final version will be soon available. All right, thank you.
And that's it. I'm definitely going to have to push for a bigger room next year. Thank you very much, Philippe. We have time for questions.
Really interesting talk. So I'm not a physical oceanographer, so the flow, everything there that's why I call people like you. But I have spent a lot of time at sea, and I've noticed that the Parcels shape seems to make a lot of difference about how they move. And so do you have any plans, in addition to incorporating size and density, but including shape in your parcel development?
So I don't have a plan, but we have a plan as a team. So I'm really working in Parcels. So it's more like the numerics of Parcels, how to interpret correctly the flow field. But us as a team in Utrecht, we use Parcels to better calibrate the data and to better track the plastics. And for this, it's easy to put into account the shape of the plastic to better to move it better. So the whole point of Parcels is to then you forget about the interpolation schemes. You forget about all the physical part. No, you don't forget. That's the main part. You forget about like all the technical details, like all the all the Python, the C code. You really have, and you can really focus on the science. So on one part, it will be like which data are you using, and on the other part, how do you parameterize your plastic behavior. And this, you can easily, if you have from some lab experiments or from some data, it seems to that such a shaped data, shaped plastics or such kind of materials behave other than some others. And you have some hypothesis why it would be the case. We can easily assess this assumption. So the idea we don't build a new behavior, but we test easily a new behavior that we have some from some lab experiment or some data. Yeah.
Very interesting talk. Have you ever thought to combine this with satellite imagery to find locations that, for example, the satellite cannot detect the ocean pollution, and then use the parcel for those regions?
So Parcels is really like to transport the particles for the simulation, but there is also like in general, not in Parcels, but in plastic in the plastics research field, there is a lot of which is done like so there are always like simulation part, like the data, like collecting data like on the field, but also there are some attempts to work with satellite data, especially also to have a better representation of the flow field. So the flow field not from comes from other models, but we can also we try that there is this planned satellite mission to be able to reproduce the surface flow field at least, including the stored drift, which is really dominating in plastics from satellite imagery. So that's the scheme project. We hope it's going to be launched, but it's still being reviewed. And on the other side, such kind of there are some attempts from satellite imagery to also to try to being able to measure plastic concentration from space, but it is completely out of my field. But I know that they're trying to do something like this. Yeah.
Changing gears more to the technical implementation. So your performance is obviously a very important consideration here. It seems like your performance and your benchmarking is oriented around the HPC environment, which I think is where a lot of us are coming from modeling, right? Mm-hmm. Have you thought about how the performance profile would look different in the cloud? In particular, it's an embarrassingly parallel problem, right? I mean, the particles don't interact with each other. So in principle, that's very well suited to like a serverless architecture where you can launch just essentially infinite number of independent processes that don't interact with each other. Have you thought about how you might be able to take advantage of a cloud architecture for scalability?
Yes, well, for this, it's not what we have designed like a directly Parcels for. So, but Parcels works fine on HPC and on your laptop, easily. We just read party somewhere and we go over the ways. We track it, but for the cloud, you could also we've been working with Willy Ras, and he was trying some desk runs, and it works fine, except there are a few problems if you go. Yeah, so here when we pass for the Python to see, so we aim to keep that for the moment because we want to work it efficiently on your laptop. But then this Python seed means that they have some pointers to the C object which are hard coded at some point in the code, and this is a bit messed up. So for that and to do long simulation on the cloud. So we would like to improve that to really. To have the links to the C object being defined as late as possible, and this will improve the possibilities of running Parcels on the cloud. But we can do it so. Basically, since particles so far are independent one from each other, you can easily break your runs into smaller runs, and then you can run it wherever you want. And of course, it will work fine. But then on the cloud, you less have the rebalancing of the parts, so you won't be as scaling as with MPI. But if you have a huge amount of data of CPU power, then you are fine with it. So it's quite easy to break up your particle sets into smaller sets and to run it wherever you have space.
Are there any plans to use unstructured grids with this program?
It's not the first priority. I would like to, because my PhD was on a structured grid, so like I would like to work to put into Parcels. But so far, the general circulation model, that they are still like highly in a structured format. So we don't have it in a structured format available now. There have been some people have used it a bit. So using our architecture of Parcels and redefining the interpolation schemes. So basically the search of where the particle is located in the grid. But I think it should arrive within the next 5 years. But we don't work on that so far, right now.
Very good. Thank you again, Philippe.
Yeah, thank you.